Some things just don't want to mix. Oil and water, right? Well, in the world of engineering, it's steel and aluminum. I mean, trying to weld them together, it's like trying to build a bridge out of crackers. It's just going to fall apart. So today, we are diving into the amazing, cutting-edge science that is finally cracking the code on this so-called unweldable problem.
It really seems like it should be simple, doesn't it? You just melt the edges and kind of stick them together. But if you've ever seen it tried, you know the result is a joint that is just shockingly weak and brittle. I mean, it'll snap with the tiniest bit of pressure. So what is actually going on down at the atomic level that causes such a complete and total failure?
Okay, so meet the bad guy of our story, intermetallic compounds, or IMCs for short. See, when you melt two totally different metals together, they don't blend into a nice, strong alloy. Instead, they form these super thin, chaotic, and incredibly brittle layers right where the two metals meet. They literally have all the strength of a potato chip, and they are the #1 reason these kinds of welds fail every single time. So, here's how we're going to break it all down. First, we're going to dig a little deeper into that mismatch problem. Then we'll look at the three-pronged attack scientists are using to beat it. These really clever chemical inner layers, some powerful external fields, and what I like to call post-weld power-ups. And finally, we'll see how it all comes together to create a true super weld.
All right, first up, let's really get into the weeds on this mismatch problem. Because, to win the war, you've got to understand the enemy. And the enemy here is brittleness.
I love this cracker and a sandwich analogy. It's just perfect. So picture it. You've got two strong pieces of bread. That's your steel and your aluminum. But the thing holding them together is a single, fragile cracker. That's your IMC layer. It doesn't matter how strong the bread is, right? The whole thing is weak because of that crumbly little center. That is exactly what's happening inside a dissimilar metal weld. So if the problem is that brittle layer stuck in the middle, how do you fix it? Well, the first strategy is to send in a negotiator. Let's talk about smart inner layers. Think of them as a kind of chemical diplomat, sent in to broker a peace treaty between these two metals that just do not get along. These diplomats are basically just super thin foils or coatings of a third metal, and you place them right at the joint before you weld, and just look at what they do. A little layer of copper helps aluminum and magnesium form much stronger bonds. A bit of zinc between copper and titanium can boost the joint's strength by over 30%. But nickel, nickel is the real MVP here. You stick it between copper and aluminum, and it acts like a bouncer at a club, actively stopping the most brittle compounds from ever even forming. It's brilliant. So you might be asking, just how big of a difference can this little diplomat make? Well, get this. The research shows that adding a tiny layer of nickel, a layer thinner than a human hair, between copper and aluminum can boost the weld's shear strength by a mind-blowing 203%. That's not just a little improvement, that is a total game changer. It takes the joint from brittle to unbelievably robust. Okay, so chemical diplomacy is kind of the gentle approach. But what if you need a little more muscle? Well, our second strategy is to use powerful external fields to physically force that molten metal to behave itself while the weld is being made. Now, this is such a cool idea. As the laser is melting the metal into this tiny little pool, you hit it with an outside force, like a magnetic field or even ultrasonic vibrations. That magnetic field acts like a tiny invisible whisk, and it starts actively stirring that molten pool. This isn't just letting things happen, it's an active intervention, forcing the metals to mix way better than they ever would on their own. And the results of all this whisking? They're fantastic. This stirring action literally shatters the large, weak crystal structures that normally form, and instead you get this much finer, stronger internal grain structure. By forcing everything to mix more evenly, you shrink that dangerous IMC layer down to almost nothing, and you get a cleaner, stronger weld with way fewer defects. Okay, so we've carefully managed the weld as it was forming. But guess what? We are not done yet. Our third strategy is all about making the joint even stronger after it's already cooled down. These are what we call the post-weld power-ups. Think of it like a workout for the metal. The initial welding process is super stressful, and it leaves the material's internal structure all disorganized and kind of weak. So these post-weld treatments, like really carefully controlled heating and cooling cycles, they're like a specialized training regimen designed to relieve all that internal stress and align the microscopic structure for maximum possible strength. Let me show you a fantastic, real-world example from a team led by Minhas. They started by welding an aluminum alloy, and they used a copper interlayer. Standard stuff so far. But then they took the finished part and plunged it into an intense cryogenic treatment, chilling it all the way down to minus 190 degrees Celsius. After that deep freeze, they applied a very gentle aging heat treatment. Every single step is methodically refining that grain structure. And here's the payoff. Look at this. The aging treatment by itself, it boosted the strength by 22% over the original weld. But when they combine the deep freeze of the cryogenic treatment with the aging, wow, that pushed the total strength increase to an incredible 54%. This just proves it's not about any one treatment, but the specific sequence that unlocks the material's full potential. And that brings us to the most important part of this whole story. The real breakthrough isn't in any single one of these techniques. Nope, it's about how they all work together. This is synergy for superwelds.
So here's the crucial point. Modern engineers aren't just picking one tool from the toolbox anymore. They are designing a complete multi-stage attack plan. They might start with a nickel interlayer, then use an ultrasonically assisted welding process to control the melt pool, and then finish the whole thing off with a very specific cryogenic and aging process to max out the final strength. It's the whole shebang.
The source research really says it perfectly. It's the synergistic contribution, that's the key phrase, of all these methods that gives engineers ultimate control. They're not just melting metal and crossing their fingers anymore, they are literally architecting the joint atom by atom for peak performance.
So, why do we care about all this complex science? Well, because being able to reliably join materials like aluminum and steel is an absolute game changer. It means we can build lighter cars and airplanes that use way less fuel. It means stronger, more compact electronics in our pockets. It unlocks a whole new world of possibilities for aerospace, for the energy sector, and so many other industries, just by letting us use the exact right material in the exact right place, with no compromises.
And that really leaves us with one last fascinating question. For decades, some material combinations were just written off as unweldable. That was it. But now that we're winning this tiny battle at the microscopic level, it really makes you wonder, what materials that we think are impossible to join today will be the basic building blocks of our world tomorrow?